So now let's say we have this integral. So the integral over some curve C of p dx plus q dy plus r dz. Right. Let's say we have this integral here. Well, notice this kind of pattern. It's a product of two things plus a product of two things plus another product of two things. That's a dot product. So we can write that down like this. Right? Because why not? All right. Well, now I'm going to call this thing f, and this thing dr. Right? So f, this is a vector field, pqr, and this thing, dr, is this guy up here, dx, dy, dz. And so that's the differential of something like this. Right? Okay, so what do we call this guy? Well, we can call this guy a couple different things. Say this is the line integral of this vector field f along C. Or could also call this a vector line integral. Right? So notice, since it's defined by these guys, then that must mean that it satisfies those same properties we talked about before, which was that it depends on more than the start and end points. It depends on the path you take between them. And also, if you switch the orientation of the curve, you're going to get a negative of your regular answer. All right? So now let's talk about what this guy actually means. All right, so let's try and figure out now, what are these integrals computing? Right? So let's say we have a particle moving in the presence of a force given by F. Right? And this can be in 2D, it can be in 3D, whichever you like. Right? Well, you might remember that if F were a constant force, then to get the work done on the particle by the force F, all we had to do was take the dot product of F with the displacement vector. But of course, most forces aren't constant, right? I mean, think of gravity. Gravity gets weaker as you get away from the planet or the object, right? So how do we do the work if, you know, we don't have a constant force, right? So let's say so let's say the particle moves along a path C, right? Then how can we actually find the work done? Well, we have to do the same kind of trick that we've done before for computing this, right? So since the force is no longer constant, this path, it could be whatever shape it wants, in R2 or R3. So let's draw a two-dimensional picture. What we're going to have to do is approximate the work little by little. Right? So let's say we have a particle moving along some curve like this. So this will be C. Right? And then how do we approximate things? Well, we know how to do it when a particle, or when we have a constant force, then we can just use the displacement. So what we have to do then is take this and break it up into really tiny pieces. All right? And then we do this in the same way we did before. Let me even call up here this pi minus 1 and this one pi. Right? So we do that kind of trick that we did before with the first line integral. But now we have to ask ourselves, how do we know, or how can we approximate the work on each of those segments now? So we have to do what's kind of like a linearization of the problem, right? So remember, work was given by the constant force dot product with the displacement vector. So let's start by kind of coming up with a replacement for the displacement vector. Or actually, let's do the constant force first, right? So just like before, we're going to come up with the sample point inside each of these. All right? So let's say in between each one of these, we do like a P1 star, P2 star, and here, this one will be Pi star. Right? And let's say we have a parametrization of this curve. So C is parametrized by R of t between A and B, right? And then what I want to do is set this up so that Pi star is the image of some RTI star, okay? And that's just like what we were doing before. So it's these sample point kind of things, right? So how do we approximate work? So the approximate work on the segment of C from Pi minus 1 to Pi, what is that given by? Well, we sample the force at that point. So the force at that point might look something, I don't know, it might be going out this way. So this would be F of Pi star. All right. So the work on the segment, or sorry, why am I putting a vector over work? The work on this segment is going to be F at Pi star. All right, but now we have to come up with a replacement for the displacement vector. All right, so the way we do this is, well, we want to take the dot product of F with something, so it needs to be something that starts at that same point. Right? So what we will do is we'll take the unit tangent vector, right? So we'll dot product F with the unit tangent vector at that point. But that, that's a length 1 vector. We actually want the length of that segment, so we have delta SI. Right? So what that does, it says, well, the particle's moving in this direction t, right? And delta SI, remember, is the arc length of the segment from Pi minus 1 to Pi. So this, in a sense, is approximating the displacement vector, right? And then the force, well, okay, so we have that force acting at that point. And remember, if everything's just a bunch of constants, work is just the dot product of force with displacement, all right? So this is an approximation of the work on that segment. And in fact, let's even make these squiggly equals. All right. So that means the total work is approximately the sum from I equals 1 to n of this kind of stuff. F at this sample point dot product with this vector. All right. Well, that's a Riemann sum, right? So the work, so taking the limit, we get, well, what we're really integrating here, so we get the work is equal to the integral over c of f dot product with the unit tangent vector ds. Right, so that's the work done by this force, F, on a particle moving along that trajectory. But let's actually write a little bit more here, because we know what t looks like, right? So this is the integral over c of F. And actually, here's what we'll do. We know the parametrization. So let's go ahead and write this out. All right, now t, remember, is just r prime of t over the magnitude of r prime of t. Right? And then ds, remember, is just r prime of t dt. So what do you notice? Hopefully you notice something. You should see that this and this cancel. So all we're effectively left with is the integral from a to b of f of r of t dot product with r prime of t dt. Actually, let's go ahead and just leave those off. Right? So, what's the big deal there? Well, the big deal is this. R prime of t dt is just dr. So, this vector line integral here really and truly does give the work done by this force on a particle moving along this curve. All right, so that's what this vector line integral is doing, and this is why it's very, very useful, and that's why this is really, the beginning of where Calc 3 starts doing major applications to physics and stuff. All right, hopefully that all made sense, and in the next video we'll do some examples. Okay, see you there.